Hello, my name is Theodore Chambers, and I'm a PhD student at the University of Notre Dame. Welcome to a presentation on our work accepted for the Proceedings of the CHI Conference on Human Factors in Computing Systems. The title of our work is HIFuzz, Human Interaction Fuzzing for Small Unmanned Aerial Vehicles. HIFuzz addresses the challenge that accidents involving sUAS, or drones, are increasing in prevalence, and furthermore, that many of these accidents involve human interactions. Depicted is an accident that occurred to one of our earlier VTOLs. In these circumstances, humans often get blamed for these incidents, even though many of them could be avoided if the systems were more tolerant to a broader range of potential human inputs. Here we see a depiction of a planned route at the top left and the actual route taken by an sUAS. Upon inspecting the flight replay, we can see that the sUAS flew north at an increasing altitude after a geofence breach. The RPIC had incorrectly set the throttle above neutral, but only slightly above neutral. Clearly, even a small mistake can lead to quite disastrous and unintended outcomes. Within our own team at Notre Dame, we've encountered numerous crashes and unforeseen incidents. A significant number of these incidents can be attributed to human mistakes or a mismatch between the software's capabilities and the team's understanding of the system at the field. Balancing mission objectives and the unforeseen challenges that arise in field deployments is consistently challenging. To this end, our work explores the impact of fuzzing in the context of drones. It is crucial to identify both known and unknown failures associated with human interactions when flying complicated missions, such as in emergency response scenarios, which is a use case that we oftentimes explore in our own research. In software engineering, fuzz testing is a broader term that explores the impact of unexpected, random, or malformed input data. The goal of fuzzing is to trigger unexpected behavior, such as crashes or memory leaks. Now, the main question we seek to answer is how can fuzzing be used safely to explore human interactions in drones? To address this challenge, we present the HIFuzz testing framework, which supports tests in 3 distinct levels, progressing from a low-cost, limited-fidelity, large-scale, with no hazard environment and proxy human agents to L2, which consists of a higher fidelity simulation with real human agents, and lastly to L3, a high-stakes, high-cost, real-world environment. Now I will describe each of these test levels in greater detail. The goal of L1 is to execute a large number of tests as quickly as possible in order to cover a broader set of test cases without any of the risks involved in real-world flights. L1 tests are consequently run in a simulator using proxy human agents instead of real humans. The L1 process starts with a planning task in which the HIFuzz tester specifies the test features that constitute the fuzz test space. These can include roles, interaction devices, drones, environmental factors, missions, and hits are what we deem human interaction tasks. Based on these definitions, we can specify an individual HIFuzz test in a way that is sufficiently formal for automating test execution, but also readable to humans who serve as participants in the testing process. We therefore utilize JSON to represent each test case as depicted in the image on the right. After defining the test features, the HIFuzz L1 system will automatically generate combinations of the properties and input values relevant to the tests, invoking the mission in the simulation environment, monitoring the runtime state of each drone, checking for preconditioned states, and delegating hits to the proxy human agent when preconditioned states have been reached. All of these steps occur automatically without human intervention, and L1 has been fully programmed as a standalone, multi-threaded system. The system mimics human input by replacing radio signals normally sent by a radio controller transmitter with Mavros manual control messages to simulate various switch changes and button presses for mode changes. Results are automatically evaluated to determine if the test passed, failed, or was untested if the drone completed its mission without the preconditions ever being met. All outcomes are then passed on to the first gateway. The first gateway down-selects a subset of tests to pass on to the second testing phase. The table at the right shows the tests selected for L2 from an interactive clustering and selection process. The number of clusters is based on a budgeted L2 testing time or based on a standard approach such as the elbow approach, which looks for the sweet spot in terms of coupling and cohesion of clusters. Typically, 1 or 2 representative tests are selected from each cluster for execution at level L2. In levels L2 and L3, humans are in the loop. L2 tests are executed in the same simulation environment. However, humans replace the proxy agents and interact with the drone through hardware devices such as RC transmitters and a GUI used in physical deployments. L2 is designed to provide higher degrees of fidelity than L1 while still remaining in a safe operational environment. We need L2 to execute tests in a higher fidelity environment and gather feedback from humans about any failures that occurred in order to better understand their impact upon human operators, and lastly, to evaluate the efficacy of user-facing mitigations such as warnings or recommendations. L2 tests are then passed through a safety assessment gateway that ensures that each failed test from L2 is carefully assessed to determine if mitigations are needed. We do not dictate how the safety assessment should be performed so long as the process assesses hazards associated with each test case, for example, by using fault tree analysis. The goal is to determine whether the risk has been properly addressed prior to testing at L3. L3 tests now strive to validate that all tests that have previously produced a failed L2 outcome have been mitigated. These final tests are in the real world and are the highest degree of fidelity, but also risky for many reasons. To engage humans in the pre-planned tests for L2 and L3, we support humans through a mobile application which is controlled by our HIFuzz test runner and provides interactive prompts to help humans mentally prepare for tasks that they need to perform and to execute those tasks at exactly the right time. We have fully developed and deployed the tool in React Native, which connects to our system over MQTT, a message bus system often used in robotics. To the left is an image of our mobile application, and to the right is a photo of an L2 test run in the simulation with a physical radio controller. Given the vast combination space of contexts and actions, we took a scenario-based approach in which we explore configurations and actions focused around a known problem area. In this example, we had experienced severe oscillations when the RPIC switched to a stabilized mode with the drone in motion with the throttle left in down position. This scenario provided a rich set of properties for us to explore. We ended up constraining the test space to approximately 160,524 test configurations, all motivated by our selected human-involved scenarios. We conducted 700 L1 tests based on various combinations of properties from our HIFuzz testing space for experimentation purposes. Each test result was flagged with outcomes including the maximum altitude reached, flight duration, landed state, and mission completion. Any test exhibiting excessive values was labeled as abnormal. For example, high altitude readings, strange arm to disarm durations, or failure to complete the mission could be classified as abnormal. Through our first testing gateway, G1, we identified 29 tests to pass on to L2. These images here depict many of the erroneous flight patterns discovered throughout this entire process. From the results of our experiments, we were able to identify many common human interaction problems for our drone system. To help identify these types of vulnerabilities, we conducted a systematic inductive analysis of our L2 test results. Some of the more common human interaction problems identified are listed here, which include incorrect throttle positions and controls, insufficient and inconsistent failsafe mechanisms, thrashing, unsafe RC transmitter mappings, and lastly, insufficient alerts. Finally, as seen in this video, we were able to execute one L3 test in the field and successfully mitigated a takeoff bug. We come to the conclusion that applying HIFuzz to our own system under test has shown it to be very effective in identifying critical human interaction vulnerabilities, and we look forward to extending it to more systems in the near future. Thank you for listening to this presentation.